this video, we will talk about conditional distribution and statistical independence. So we have learned that if we let two events A and B, though their probabilities, the conditional probability of B given A can be denoted by PB bar A, can be defined as the division of PA and B by PA. So PA means the probability of A occurs, and PA intersect B means the probability of both A and B events occur. So when we have learned the random variables and probability distributions for the two random variables, we can also write probability of y equals y given x equals x can be expressed as the probability of x equals x and y equals y divided by p x equals x. So here, for the discrete random variables, we can write in this form. And for the continuous random variables, we can write fxy divided by gx, where fxy is the joint probability density and gx is for density of x. And it is not difficult to show that the function fxy divided by gx is strictly a function of y with x fixed, and it also satisfies all the conditions of a probability distribution. So this type of distribution is called a conditional probability distribution, and the definition is: let x and y be two random variables. They can be discrete or continuous. So the conditional distribution of the random variable y, given that x is fy bar x and equals fxy divided by gx. And similarly, the conditional distribution of x given that y equals y can be expressed as fx bar y equals fxy divided by hy. So gx, hy are the marginal distribution of x and y. And fxy are the density function for the two-dimensional density function for x and y. So if we want to find the probability that the discrete random variable x falls between A and B when it is known that the discrete random variable y equals y, so we can calculate probability of x between A and B when y equals y is the summation of all the conditional probability of x given y then over the range of x between A and B. And for the continuous case, we can write probability of x between A and B given y equals y is the conditional density function fx given y, take integrals of dx over the range A and B. So we take a look at an example of conditional distribution for the discrete random variable case. So two ballpoint pens are selected at random from a box that contains 3 blue pens, 2 red pens, and 3 green pens. If x is the number of blue pens selected and y is the number of red pens selected, find the conditional distribution of x given that y equals 1 and use it to determine the probability of x equals 0 given y equals 1. So the solution is, so first we can calculate the joint probability distributions for each possible values of x and y. So we list this table using the formula if xy equals division in the denominator is all the combinations of 8 balls, select 2 balls, 8 balls because we have 3 blue pens, 2 red pens, and 3 green pens. So there are total 8 pens. We select 2. They are all combinations of 8, 2. Then in the numerator, there are the 3 parts because the balls, 8 balls, has been grouped in 3 different colors. So this represents 4 blue pens. Because from 3 blue pens, we select X blue pen, right? From 2 red pens, we select Y red pens. And from 3 green pens, we select 2 minus X, 2 minus X minus Y green pens. So there are total different combinations. Then can be calculated as the probabilities for each case. So the table lists all probabilities for each different x and y and their marginal probabilities and total probability summation will be 1. So next will be easier. So we first find the marginal probability for hy equals y equals 1. Then we just sum all fx1 to fxy when y equals 1 here. So there are about 3 of 7 is h1. Then further we can calculate the conditional distribution of x given y equals 1 is this table because when y equals 1, different fx1 can be calculated from the table. When x equals 0, 1, 2, then we fill in this table. This is the conditional probability when y equals 1 and x, the value for x. So finally, we can find when y equals 1, x equals 0's probability is 1 of 2. So next, show an example of continuous conditional distribution for the continuous random variable. So the joint density for the random variable x and y, when x is the unit temperature change and y is the proportion of spectrum shift that a certain atomic particle produces, is fxy. The joint density is 10 times x times y squared for the values 0, less than x, less than y, less than 1. And density is 0 for elsewhere. So the question is, find the marginal density gx, gy, and the conditional density fy given x. Then question B is find the probability that the spectrum shifts more than half of the total observations given that the temperature is increased by 0.25 units. So the solution is by conditional probability density definition. So we can first calculate the marginal gx using the integral of fxy over y for all available value of dy. Then fill in the form and we take the integral from x to 1 dy. Then we'll get the result is this. And for the x values 0 less than x less than 1. And similarly, we can calculate the marginal distribution for the y equals this one. And for the available y value between 0 and 1. So now the conditional distribution of y given x can be calculated as fxy divided by gx. So the result is 3y squared divided by 1 minus x cubic. And available x and y value is 0 less than x less than y less than 1. So therefore, we fill in using this conditional form, we fill in x equals 0.25 and y larger than 1 of 2, can take the integral, and after mathematical manipulation, we can get a result of 8 of 9 for the question B. And next we talk about statistical independence. So if we let x and y be two random variables, they can be discrete or continuous. So with the joint probability distribution fxy and marginal distributions gx and gy. So the random variables x and y can be said to be statistically independent if and only if fxy equals gxhy. So which means statistical independence exists when joint density or joint probability distribution equals their projection multiplication of the marginal distribution for all xy values within their range. So this means the conditional probability f x given y does not depend on y, and outcome of the random variable y has no impact on the outcome of the random variable x, and vice versa. So we look at an example for the statistical independence. So first, given the joint density function, this one fxy, then for available value for x and y, and question A is find gxhy and fx given y and prove x and y are statistical independent. So the solution is, for the definition of the marginal density for this available value for x and y, can calculate gx marginal distribution for x and marginal distribution for y, we get a result of these two forms. Then we times these two together equals fxy here for the available value x and y. So because the product of the two marginal distributions gives the joint density function, so the continuous random variable x and y are statistically independent. Another example for the statistical independence, suppose that the shelf life in years of a certain perishable food product packaged in cardboard containers is a random variable whose probability density function is given by fx equals e minus x in power when x larger than 0 and 0 elsewhere. So let x1, x2, and x3 represent the shelf lives for 3 of these containers selected independently, and find the probability of x less than 2, x2 between 1 and 3, and x3 larger than 2. So the solution is, because the containers are selected independently, we can assume that the random variables x1, x2, x3 are statistically independent. So we can have the joint probability density is fx1, x2, x3 equals fx1 times fx2 times fx3. So actually in this form, e minus x1 minus x2 minus x3 in power. So for For these values, we can calculate probability of x1 less than 2, x2 between 1 and 3, and x3 larger than 2. We can just take 3 steps of integration over dx1, dx2, and dx3. Then the result is about 0.0372. Thanks for watching.